welcome to the protein quiz. This is a big, last important chapter. What do proteins do? Why are they important? They do everything. So one kind of a protein is an enzyme, which catalyzes a reaction. So my hint about question one is that it takes a lot to keep an enzyme functioning. So this question, you could see it as an opportunity to learn some things, a list of things about enzymes that you might not have known before. There's a similar situation with question two. I think I made a video that talked about a few of these things. What specifically about their names are we looking at? The ending, ACE. For number 4 here, for a lot of general reactions, if the word enzymatic weren't in here, we might think that most general reactions just go faster at higher temperatures. But remember, enzymes are kind of fragile, and they need some specific conditions in order to function. And remember that they do function well at your body temperature, which is 98 Fahrenheit or 37 Celsius. You can remember that because there was a boy band called 98 Degrees, but in Europe they would have been called 37 degrees. This is a true-false, so I don't really need to talk about it, but if an enzyme added water to something, you might call it a hydrolase. That same video I already referred to talks about how an enzyme works. And if it were to increase the activation energy for a reaction, the reaction would go slower. Okay, let's just go through the first few of these and see what we think. Okay, an apoenzyme is just the protein part without the prosthetic group. This is basically a protein lacking the part that isn't an amino acid. And effector is not a key term from the chapter. This is kind of a random made-up word. A mineral is an inorganic substance. But the last several chapters have been about organic chemistry. Proteins are organic molecules. That's a good start on that one. Okay, so looking at the name here, D, that means it would remove something. It takes off carboxyl. And remember, our carboxylic acid has a carbon and 2 oxygens as part of that functional group. This is one to refer to my video for. It'll be pretty easy if you watch that video. For 21, I'll repeat what I said at the beginning, which is proteins do everything. All right, an alpha helix, that is a kind of secondary structure for a protein. And let's see, so it's important to know that. Covalent bonding, maybe disulfide bonding would hold together the tertiary structure of a protein. Disulfide bonding is a kind of covalent bonding. And then let's try to eliminate this one. Coordinate bonding, that involves a metal, so we can eliminate that one. Since a metal is probably, it's not part of a lot of proteins. It's not an amino acid. Metals are not in amino acids. All right, number 24, vitamins. They always have less than 4 atoms. Those would have to be very, very small molecules. There's only just a few organic molecules that have less than 4 atoms. Make up coenzymes, which are necessary for the function of an enzyme. That sounds reasonable. Maybe we'll come back to that one. They completely destroy the ability of most proteins to function. They would be highly poisonous in that case, and you would die if you took vitamins. competitive inhibitors are also bad, so they'd be poisonous too if they were inhibitors. And I think we eliminated at least some of those, but not all of these. I've already answered question 25 recently in this video. Okay, now we're getting to the part that I really need to explain a little bit about. So the next few questions I think are going to match primary, secondary, tertiary, and quaternary structure. Multiple, often identical proteins coming together is a that's quaternary structure. I'll just go ahead and tell you that's what that is. The sequence of amino acids. So before any folding happens, before you know if there's any alpha helices, beta sheets, or whatever, you get that primary structure, which is just the which amino acids are there and in what order. Okay, when a protein's denatured, what happens? It unfolds, right? So it can't be that all of the secondary, tertiary, and quaternary structures remain intact. Some of those have to get altered, or else the protein's fine and it's still in the right shape. Yeah, and it's a problem for you if the protein denatures, because it will take the wrong shape and will not be able to function very well. Remember, hydrogen bonds are important in secondary structure. Okay, we're looking for quaternary structure here. What we have at the top answer here is these three letters are they indicate amino acids. So here's one, here's another. This is the sequence of amino acids. This is the primary structure. Aspartic acid, lysine, those are the three-letter abbreviations for amino acids. Identical peptide subunits, that sounds like quaternary structure. Alpha helix and beta sheet, those are two kinds of secondary structure. And we'll get to this one in a minute. I just answered this question 2 seconds ago. Okay, now here's a confusing one. We're looking for tertiary structure. We've decided that the sequence is primary. Alpha helix is an example of secondary structure. But the tertiary structure, it involves how the helices and sheets orient relative to each other. And this garbage here is supposed to represent the order of sheets and loops and how they orient relative to each other. So that's what this is the answer you're supposed to decide on for this question. We're looking at this one here as the correct answer for tertiary structure. Remember, a catalyst speeds up a reaction, and this chapter is about protein. So we can narrow it down probably to some kind of protein, right? I guess enzymes are also, if you didn't know, they are a type of protein. All right, let's assess these answer choices. Hemoglobin and myoglobin. We saw that hemoglobin moves oxygen, myoglobin stores it. Maybe. Let's come back to it. Collagen and pepsin. Let's just look at pepsin. This is the enzyme in your stomach that breaks down protein. Keratin, that's in your nails, like fingernails, toenail. And last but not least, we got a good question here. So, quick crash course on amino acids. Every amino acid has these three atoms in a row: nitrogen, carbon, carbon. And the nitrogen on the left is an amine nitrogen, and the carbon on the right is a carboxylate carbon. So in fact, every amino acid, well, if it's on its own, has a kind of backbone that looks like this. But what can be different between the amino acids is what is sticking off of the middle carbon. And in fact, what that is different in every amino acid. So every amino acid has a different group here, and we call that the side chain or